talk about dynamic programming and memoization. Now that is not memorization. There's no R in there. Memoization means creating and storing and reading memos. All right, now let's look at an example of where this comes in. A well-known example of a recursively defined sequence is the Fibonacci sequence. F1, F2, F3, F4. F1 is 1, F2 is 1, F3 is 2, F4 is 3. And every subsequent number is the sum of the previous two. 2 plus 3 is 5, 3 plus 5 is 8, and so forth. They grow exponentially. Now, this is the recursive definition. F2 and F1 are both 1. Well, for larger n, Fn is Fn minus 2 plus Fn minus 1. Well, this means, based on this recursive formula, there's an obvious recursive function we can code of type integer. We'll call it fib. It takes one parameter, an integer called n. And if n equals 1 or n equals 2, we return 1, because fib 1, F1 is 1, and F2 is 1. Otherwise, we return fib of n minus 2 plus Fn minus 1, just here. And is this program correct? Answer, yes. Should you run it? Answer, no. Why not? Who can tell me why not? Because this takes exponential time. As n grows larger, if you ran this with fib 100, you would be waiting, well, I won't say till the cows came home, because the cows would all be extinct by that time, and we would have gone on to a different species, because it would take an enormous amount of time. So we're going to do instead something called memoization. Now, using this recurrence relation, we can quickly write a dynamic program to compute Fn. Let's suppose that we're given an n and we want to, so therefore we can run this program and it will compute f of n for us. So if our goal is to get f of n, we can do this within n time, which is a lot better than the exponential time we got. There's another recursive formula for the Fibonacci numbers. Fn is the product, the sum of two products of lower Fibonacci numbers. But these four Fibonacci numbers are not unique. There are actually only 2 or 3 of them. If n is even, there are only 3 distinct values, and if f is odd, there are only 2 distinct values. Because we're doing rounding here, truncating down. So f of a is f3 times f4 plus f4 times f5. Well, f of 9 is the square of f4 plus the square of f5. So it's only 2 values. So that we can then, using dynamic programming,
Pause.
this dynamic program will compute f of n. And for all I from 1 to n, if I is 1 or 2, you return 1. You set the value of the array equal to 1. And otherwise, you set the value of the array by fetching previous values of the array. And that simply uses this recurrence to define all the f's all the way from 1 to n. So this particular program takes theta of n time, just like the other one. Now, here is where we can draw this tree for F100. F100, this is now a directed graph where these are drawn in topological order. F100 depends on the values of F49, 50, and 51. Well, those 3 values depend on these 3 values, 24, 25, and 26, where the line represents a dependency. Meanwhile, these three values depend on these four values, F11, 12, 13, and 14, which depend on these four values, F5, 6, 7, and 8, which depend on these four values, 2, 3, 4, and 5. Now 5 is also a repeat, and then continue it down here, this F3 is F1 plus F2, and the F1 and F2 are, of course, 1. Now this means that in order to compute F100, I don't really need to compute everything up to 100. I only need to compute the values of F that are on this table. I can do that dynamically by computing first F1, then F2, then F3, then F4, then F5, then 6, and 7, and 8. I would skip 9 and 10 though. I do 11, 12, 13, 14. Then I would skip everything from 15 to 23 and do these. Then I would do another skip and do these three and then skip way up to 100. But what's the problem? The problem is I would have to know in advance which ones to skip. Now, the way we can save time, if we try to do it recursively, using the new recursion, it'll still take exponential time. If we do it dynamically, it'll take linear time, O of n. Can we do better? If all we want is f of n, we don't have to compute all the Fibonacci numbers up to that. But how do we know which ones? Well, we're going to have a sparse array, and the items in the sparse array, the ordered pairs, I, f of I, are called memos. And there will only be relatively few memos compared to the number of possible memos, which is n. There will only be a much smaller number. And the sparse array, we have to be able to tell whether the value of fi has already been computed. So the way that we work, the way the sparse array works, is a program that looks like this. We input the index, and the first thing we do is ask whether this has previously been computed, whether fi is a value we already know. And if it is, we return that value, and the program ends, the subprogram ends. But otherwise, we store the new value. We compute f of I to be this formula, and then we store that value, and then we return that value. Now, of course, each of these is a recursive call to the same function. But if any of these have already been computed, they don't have to be recomputed. So it could be that each of these takes just finitely many steps. Now, the question is, how many different values do you actually compute? Now, remember, there were a bunch of layers, and each layer had at most 4 values. And how many layers were there? It turns out the number of layers is O of log n. And so the time complexity is theta of log n. That is a gigantic savings over f of n, over O of n.